So we get a couple of formulas for multiplying and dividing. Note, in order to use these, we need to have polar form. So one of the reasons we spent all this time looking at polar form is so that we can use these quick product and quotient formulas. Note that in order to find products and quotients without these, we would need to FOIL. Not that FOIL is the end of the world, but eventually we'll be looking at things bigger than just multiplying 2, maybe multiplying 3, maybe taking something to the third or the fourth or the fifth power. There are going to be very quick formulas we can use that are much faster than pulling out that binomial theorem and Pascal's triangle. So our product formula, once we have our two complex numbers in polar form, I'm actually going to go ahead and switch to blue. So we'll do blue and green here. What we need to do is multiply the two moduli together, so R1 times R2. And then on the inside, the arguments get added. So then we wind up with cosine of theta 1 plus theta 2. The same thing will happen inside of sine. So there's still an I hanging out, and then the argument of sine will be theta 1 plus theta 2. So that is how we multiply two complex numbers in polar form. Again, instead of a big FOIL process, it becomes a quick multiplication and a quick addition. So, as you might be able to guess, the quotient formula is very similar. But since we're dividing, instead of multiplying R1 times R2, we want to divide R1 divided by R2. And instead of adding these two angles together, we will subtract them. So if we want to boil this down into just a quick bit of English here, to multiply, we're going to multiply the moduli and add the arguments. To divide, we will divide the moduli and subtract the arguments. So let's look at a couple of examples. Switching over to the whiteboard so we can add a bit of color here. Notice we are multiplying these two complex numbers together, and they're both in polar form. So they have that modulus and that cosine I sine with an angle that's our argument. So in order to multiply these two things together, we're going to multiply the moduli and add the arguments, which is fancy nerd speak for multiply green stuff and add blue stuff. So our two moduli are 2 and 6. Those get multiplied. And then we still have a cosine and an I sine. We're going to add those arguments together. Cosine and an I sine, leaving myself a lot of room here. Cosine of, and our two angles are 5 pi over 4 and pi over 2. We'll have the same thing here for the I sine portion, 5 pi over 4 and pi over 2. So there's a bit of work to do to simplify this. We do have the multiplication. That part's not too bad. 2 times 6 is 12. The part that's usually a bit more of a struggle is when we have to play around with these fractions a little bit. Note that right now we do not have common denominators. We have a 4 and a 2. Before we can add those, we do need to get common denominators. So we can rewrite pi over 2 as 2 pi over 4. And now we can add these together. 5 pi over 4 and 2 pi over 4, those do have common denominators, so we're good there. So 5 pi over 4 plus 2 pi over 4 will be 7 pi over 4. And then we'll get the same argument for the I sine part. So while it looks like there's really 3 things that we need to simplify here, it's really just 2. Because the angle is going to be the same for both the cosine part and the sine part. So that's our product. Multiplying these two complex numbers together, we get back that product in polar form. Unfortunately, they didn't ask us for the product in polar form, they asked us for the product in rectangular form. So pay attention to instructions. Sometimes you're asked for one, sometimes you're asked for the other. If we're just asked for polar form, we're done. Unfortunately, we need to convert this thing to rectangular form. So converting to rectangular form here, I have cosine of 7 pi over 4. Really helpful to have a unit circle here. 7 pi over 4 is in the 4th quadrant, so cosine is going to be positive there. The 12 still hanging around. Cosine of 7 pi over 4 is root 2 over 2. And then the I sine portion, don't lose that I. There is still an I there. Sine of 7 pi over 4 is negative root 2 over 2. Again, 4th quadrant, so sine is going to be negative. One last step then to get this into our rectangular form. Note that we have this 12 on the outside. We can distribute that 12 to both of these values inside. And after that distributive property, we are good to go. 12 on top, 2 on the bottom, that's a 6. This will leave us with 6 root 2. And then we don't want to lose that I in the second part. We'll have 12 times that second term. Note there's a negative here, so we can go ahead and just make that a negative 6I root 2. And again, that is our rectangular form. So two different forms, they both represent the same complex number. We want to be comfortable going back and forth between these two different worlds. But at the core, that's what a multiplication problem looks like. Multiply moduli, add the arguments. Let's do another one. So another multiplication problem here, multiplying one complex number in polar form by another complex number in polar form. Same process as last time. We want to multiply the moduli, the numbers in green. So that's a 5 times 2. And we're going to multiply that by this big old set of parentheses here. We're going to add our two arguments. So I'm going to have a cosine of 11 pi over 6 plus 2 pi over 3. And then I'll also have an I sine. Same two arguments. Leave myself a bit more room there. So we're going to add those two angles inside of cosine. And then we'll do the same thing inside of I sine. So we multiply the moduli, we add the arguments. Simplifying this a bit, 5 times 2 gives us 10. And just like in the last example, we have 11 pi over 6 and 2 pi over 3. They do not have the same denominator, so we need to clean that up a little bit. Not too bad getting it. We can rewrite 2 pi over 3. We can rewrite that as 4 pi over 6. So 11 pi over 6 plus 4 pi over 6 gives us 15 pi over 6. If that's driving you nuts, that's okay. 15 pi over 6. That can be reduced. Take care of that in just a second. Inside of I sine, we're going to have that same thing, a 15 pi over 6. But now 15 pi over 6 can be reduced. Both 15 and 6 have a factor of 3 in common, so you can reduce both of them by 3. 15 divided by 3 is 5. And 6 divided by 3 is 2. So, in the interest of board space, I'm going to do that right here. You might want to rewrite it. So keep in mind, if they were asking us for polar form, we would be done. That is the polar form of this product. No big deal. However, they didn't ask us for polar form. They actually wanted rectangular form. And in order to get that rectangular form, there's a bit more work to do. Note we have this 10 on the outside of the parentheses, so we can distribute that 10 inside. And we have to evaluate both cosine and sine of 5 pi over 2.
If this is still bothering you, 5 pi over 2, you can think about, what's that coterminal with? Because again, if you pull out your unit circle, 5 pi over 2 is not going to be an angle on that unit circle. But 5 pi over 2, well, that's once around the unit circle, and then pi over 2 more. So this will be the same thing as evaluating cosine of 1 pi over 2, and that is going to be 0. So we'll have a 10 times 0. And then we'll also have 10 times I sine of 5 pi over 2. Again, sine of pi over 2 is the same thing as sine of 1 pi over 2. And that's going to be a 1. So we'll have a 10. Ooh, let's keep our colors consistent. So we'll have the 10 coming from the modulus. And then we will have the I, which is already there. And then sine of 5 pi over 2, same thing as sine of 1 pi over 2. That's just going to be 1. So when it's all said and done, when we go to simplify this, get this in the simplest form possible, 10 times 0, those go away. Anything times 1 is just itself. So this one, a little bit cleaner than last time. Our rectangular form is just 10i.